at a few things today, but to start off looking at something called a phase shift. We take a start looking at a simple sine curve, and we translate it so 30 degrees. Well, this is just a regular horizontal shift. But in particular, this is on a periodic function. And we give that a special name called a phase shift. Let me show you, if I were to do a phase shift of 2 pi, what do I get? I get my function back. I've shifted it, I've done a phase shift the entire period, so I get my function is repeating. Nothing really happens. If I were to shift this just pi, well, on one hand, you could look at this as a translation. So we're translating it to the right pi, but you might notice that this is also just the sine function turned upside down. If I were to write negative sine x, okay, it's just going to overlap it. So if I give just the right amount of phase shift, that wasn't it. No, over 2. We would recognize this function. It's a cosine function, yeah. So again, while the phase shift is just a horizontal translation of the function, because it's periodic, there's some tricky things about it. I want to alert you to a very common error. So, say I put on an exam, I say I want you to graph this function. 2 sine of 3x plus pi. So, a very common, change that. So a very common thing I would do, I would, the xy axis, notice a sine function with an amplitude of 2, and my period is no longer 2 pi, it's 2 pi over the absolute value of b. So I know its period is pi. Just going to graph this part, ignoring this for the moment. So if this is pi, and this is pi over 2, so my function will look like this. It's got a period of pi, it's got an amplitude of 2. see I have a pi here. I've shifted it clearly to the left pi. So I would think, okay, everything kind of moves like this. And that would be my graph. But I would have made a mistake. I would have made a very important mistake. Just trying to catch up here. Okay. So does anyone recognize what my mistake is? I think the other day I talked about the idea of a sine of b times x minus c plus d. Anyone see where I've gone wrong here? Okay, yeah. Yeah.
Did you not contract it?
Contract?
Yeah. Because of the 2 value?
No, I found that the period here is 2 pi over absolute value of b. I'm calling this b. But this is not in the same form as this, right? See, this is 2x, but this is just plus pi. Really what I want to do is I want to put parentheses around here. And to do that, I have to make this pi over 2. That is to say, my phase shift is not pi, it's pi over 2. All right? It's just a very common error you should be aware of. Don't make that error, of course. All right. So we want to make a few kind of non-mathematical observations. Fine, yeah. Here we go. So I think everybody's familiar with, should be familiar with these plugs. We plug into the wall, plug into our electricity, and the power coming out of these, we get a voltage that oscillates as a sine wave, has a period of a 60th of a second. We call it 60 cycles per second, or 60 hertz. That's standard in the US and in a lot of places in Europe. Well, we have 110 volts that's oscillating at that rate. In Europe, I think they have 220 or 240. Canada, it's 50 hertz, some places. If you go somewhere like Europe, you'll see they'll have a different plug trying to keep them from frying your electronics. You can get 220 volt in the US. That's a different plug too. If you have an electric dryer, it'll kind of look like this. But I'm mentioning this because there's another standard you might run into in the US. It's kind of an industrial standard. It's unlikely you have this in your home. But it's called three-phase. You notice the plug has 4 different connectors. One of them is a ground, and then 3 of them have a voltage. But the voltages, which are 240 volts, are out of phase, right? Or they have a phase shift of 1/3 the period, or we call that 120 degrees. The entire period would be 360. And this is a diagram showing the voltages on these lines. You'll notice that they kind of overlap. What's this about? I mean, this isn't a physics class, so this isn't real important to understand, but what you get when you do this is instead of kind of a changing voltage that your electronics has to adjust to, the power coming through kind of oscillates as it's moving. Here we have these three overlapping voltages, so you can get kind of smooth power out of it. And again, typically this is an industrial application. Probably could put one in your home, but you'd have to pay a lot extra to the power company to put it in. But this is just a good example of a phase shift where each of these three wires down here, I don't know which one is the ground, but assuming this is the ground, these three wires each have a voltage going out of phase. So, okay. I think that's most of what I wanted to say. Graphing sine functions. Okay, any questions? I'll come back to this. Any questions on what each of these variables A, B, C, and D mean now? Yes?
So that is how it's graph over the side of the blue?
This one?
Yeah.
No, because I didn't fix it. So I originally drew it with a 1 pi phase shift, but it's really a minus pi over 2 phase shift. So let's see, this is going to move over a half. So again, it's just relative to the regular sign, it's just going to move over.
So that pi over 2 right there, that's, or what is that?
In other words, initially, usually a sine function starts at 0, but this sine function is going to start at pi over 2. This has a period of pi because of the 2 here. That's the 2 pi over b. That tells me the period. Okay. Moving onward. Okay. I'm going to switch gears a little from the sine function. I haven't said much about the cosine function, it's because, as you can see, it's just the sine function with a phase shift. But I do want to talk about the tangent function. Our tangent of theta is, of course, our sine theta over cosine theta. And before I actually try and graph it, I want to go back and look at my unit circle. And let's look at a few points on here. At 0 degrees, the sine is 0 and the cosine is 1. So here the tangent will be 0. 45 degrees, we have point 1 over the square root of 2, 1 over the square root of 2 for the sine and cosine. So the tangent is 1. And then when we get up to 90 degrees, what happens? Well, with 90 degrees, the cosine is 0, so the tangent, write this in, the tangent of 90 degrees is undefined. It's going to be dividing by 0, so what happens with a function when you divide, where there's a point where that function gets divided by 0? What do we usually find there?
A hole?
We could find a hole.
Undefined.
Well, it is undefined. I'm thinking when we graph it, what do we call it for a rational function? Yeah. Yeah, we get an asymptote, right? If I have like 1 over x minus 1, at 1 you're going to expect the function to head up there. Because as it gets close to 0, this gets larger and larger. Same thing is going to happen here. As we move back over to 135 degrees, these two values are now opposite, so the tangent will be -1. Again, back down in 180, it'll go to 0 again. Here, with both the cosine and sine negative, the tangent will be 1 again. And again, down here, we're going to divide by 0, so it's undefined. And at 45 degrees, it'll again be -1. So what I want you to notice is that I haven't put in enough values really to see this clearly, but we start at 0, we move up, we become undefined, right? Then we're negative, and we go back down to 0. We go back to 0. Then we're 0, and we go back up to 1 and up to undefined again. It's like we're repeating what we did over here, which is to say we might expect the period not to be 2 pi. It's going to repeat more often. It's going to repeat every pi. So, okay, let's take a look at what Desmos would do with this. Okay, it's interesting. Just going to draw a little of this on the board here. So, at 0, of course, we found it's 0. At pi over 2, it's 1. And also now at negative pi over 2, we can see it's going to be -1. That's this point over here. Pi, where the cosine is 0, we have an asymptote. Same thing at negative pi. It seems what this function does is it kind of moves up asymptotically. But then it repeats, right? It repeats every pi. So we have this phenomenon of periodic asymptotes. Okay, so this is the graph of the tangent. Tangent of x on my xy coordinates here. Okay, so I have a few questions. Some of them I've answered already. So the first question is, where is this function not defined? Asking kind of the inverse of where is its domain. So where can I say x is not going to be defined? Okay, yeah, that's 3 pi over 2. Yeah, that's pi over 2. That's correct. It's not defined there. I want to know everywhere it's not defined. I think we see pi over 2. Negative pi over 2. Negative 3 pi over 2. How would we describe that? Pi? Yeah, but it's every pi n, but we have to start somewhere, so we can just start at pi over 2 plus pi n. And that's precisely where cosine of x equals 0. Okay, what's the period of this function? Yes, Steve.
Is it 4 pi over b?
4 pi over
b? Are you asking for the formula, or are you asking for the...
I wasn't, but I'm glad you said that. That's right, this is tangent of bx. Right now b is 1, but that's okay. So then you would say the period 4 pi over b would be 4 pi, right? I think you had the right idea, you just went in the wrong direction. Yeah, it's just pi over b, right? The period for this function is pi, but if we have tangent of bx, it's just going to be pi over b, or the absolute value of b. So that's a difference between this and the sine and cosine. It repeats more often. Do you have a question, or?
Wouldn't you kind of, I know that you call them like sub-intervals, you have the 2 sub-intervals, or is that similar to?
I don't know how to apply that here.
So like if you did, I guess, graph any, like sine or cosine graph, you like get the interval of what it is and divide it by its sub-interval. That makes sense. I don't know if I'm asking right.
Don't feel like I know what I'm talking about. I don't understand how that would apply here. Let's just say that the period for the tangent is pi over the b value, where b is the number here that you multiply by x minus whatever the phase shift is. Yeah.
So the last one, you said it was 2 pi over b, the last one was pi over b.
You have to be very careful with why questions. The last one was a sine curve, right? So it's going to look as 1 minus 1. So what is it going to do? It's going to come up and then go through pi and then down through 2 pi. So it doesn't repeat until it's gone through 2 pi. right? The tangent only takes, I mean, we could start anywhere, it's periodic. We like to start here because it's not defined here, but we could start here. It kind of goes up, and then it kind of comes from up to here, right? And then it repeats. That only takes pi. So what I'm trying to show here is that because the sine and cosine go up and down out of phase, when you combine them in this way, you actually decrease the period. I don't know if I demonstrated that clearly enough. But it is a fact that the period here for just the tangent function is going to be pi, or if we have a b value, pi over b. Is that okay? All right. So what is the domain of this function? I guess we kind of answered that when we said this is where it's not defined. So we could just say the domain is all reals with x not equal to any of these. So that's the domain. What's the range of this function? Someone in the back row, yeah.
Is it negative infinity to infinity?
Yeah. We have a simpler name for that. We
All
can say
reals.
all real numbers. Yeah, excellent. Yeah. Okay. When we talked about the sine and cosine, our a value, say a sine of x, we called an amplitude. If I put an a in front of the tangent, well, it does something to the graph, right? It stretches it out. But it's not really an amplitude because no matter what we do, the tangent function is going to go to infinity and negative infinity. You will see sometimes in a book they'll call this the amplitude, but just keep in mind it's not a limit on the range of the function. All right. I'm going to digress for a minute. Come back to these graphs for a second. For about, you know, I like you, I took pre-calc probably once in high school, and then took geometry, and I just wondered, why is this called the tangent? It's called the tangent. I mean, we already use the word tangent for something else, right? We already have a meaning to that word. Mathematics will sometimes reuse words. Usually they try and, if it's not the same thing, at least it should evoke some kind of idea. But when we think of a tangent, we think of a circle and some line that just touches at one point. And I don't know if you recall, but the tangent is always going to be perpendicular to the radius at that point. Later in calculus, we'll use a more expanded version of tangent. You could have a tangent to a more general curve than a circle. But here's the idea. We have a unit circle. Its radius is 1, of course. We have some angle theta. And so its y-coordinate here is, of course, the sine of theta. So the length of this side is the sine of theta. The length of, the length of this segment, because it's the x-coordinate, that's the cosine of theta. Now, if I were to extend this ray, well, rays are already extended, right? And I were to draw a tangent to the circle here, this ray would intersect this tangent at some point. Okay, let's give these points here some names. We'll call this A, B, D. Call this intersection C and this intersection E. And we know from simple geometry something about similar triangles. We have two similar triangles here. We have ACB. And that's similar, I think that's the similar symbol to AED. Well, why is it? Well, this angle is in common, this is a right angle, so the third angle has to be equal, so they're similar triangles. So if you have a similar triangle, you can say something about the ratios of their sides. In particular, you can say BC is to AD. That's the sine over the cosine. That's going to be similar to ED over AD. But as I pointed out, this is the sine over the cosine, right? This is sine over cosine. Or the tangent of theta. Okay, so we have here that ED over AD is equal to the tangent of theta. This is the point where somebody's explaining something, they say, but wait, what is AD? It's 1. Right. So this is just saying that the length of ED is the tangent of theta. Aha! The length of this tangent is the tangent of theta. So as far as I can tell, that's why they call it the tangent. It took me 40 years to run that down, but now you have it from the start. Yes, Carlos?
Can you put down the desk? Can you put down the desk?
Oh, sorry. I'll have to put it up again. Yeah. So ED is the tangent of theta. The length of ED is the value of tangent of theta, and it's a tangent. Okay. Next thing I want to look at, because it's keep on looking at the board. Oh no. I locked myself out. The next thing I want to look at is the next function in our list, which of course is the cotangent. Desmos likes COT, not CTN. Okay, so keep in mind the red line is the tangent, right? It's going through 0 here. And what does it look like the cotangent? What's the cotangent doing? Well, it's upside down, right? Let's see if I can do this. If I take the tangent, which looks kind of like this, and then I turn it upside down. Well, how would I do that? I would take the mirror of it in the y-axis, so I multiply it by -1. So now, here's my minus tangent of x. And then what do I have to do with it? It doesn't go through 0. Where does it go through? Let's take a look. It goes through pi over 2. So if I take minus tangent of x minus pi over 2, that's my cotangent. And you can see from the graph, it has very similar features. Again, I have my list of questions. So where is it not defined? Where is the cotangent not defined? Well, apparently there's a point, oh, it's at pi over 2, right? It's definitely not defined. Move this, move it over to pi over 2. Is that right? I think I'm making an error here. No, it's moving it over pi over 2. Okay, oh, okay, so it's not defined, it's not at pi over 2, it's at pi and 0. And that repeats, right? 2 pi, 3 pi, negative pi. So it's undefined at these places. That's where the asymptote is. If you recall, we defined the cotangent as the cosine over the sine. So these are precisely the points where sine is equal to 0. What's the function's period? Pretty easy. Yeah. It's just like the tangent, it's pi. Or if you have a b value in here, you know, cotangent dx, it'll just be pi over b. Okay, domain, of course, is just all reals except these. And range again. Just want to remind me of what Harold said a few minutes ago. It's all real numbers, yeah. Goes up, goes down. Okay, we're almost through these functions. Yes,
When
Carlos?
is the y not all real numbers?
I'm sorry?
When is the y value not real numbers? Or when is the...
I mean, when does a
range?
function
When's the
have a
range?
range which is not all
Yeah.
real numbers? Well, the sine function and the cosine function have a range of what? sine and cosine are just the coordinates, right? Sine theta, sine theta. They're just the coordinates on this circle, whose it's a circle of radius 1. So this is the equation of that. So what's the range on sine and cosine? $50 question here. Yeah. It's just, well, negative 1 to 1. Right? So that's an example where it's not all reals. We're going to see another one right now. Right. So let's look at the out of order, but let's look at the cosecant function, which is 1 over which function? Henry, you know which functions? Sine. Okay, so if you are requested to graph the cosecant function, I highly recommend that you start by not graphing the cosecant function, but graphing the sine function. You will see why momentarily. If I first graph the sine function, then I know a few things, right? For example, I know the sine function is 0 at 0, 0 at pi, 0 at 2 pi, negative pi, and so forth. So what would I expect for the cosecant function at those points? Which, if I'm going to be dividing by 0, what would I expect? Well, it's undefined, right? 1 over 0 is undefined. What do we get with a rational function at 0? Do you want to answer? Get an asymptote. Okay. This is 1, 2. Okay. What do we know about 1 over some number? Well, sine of x is between, let's just say between 0 and 1. 1 over a number between 0 and 1, what's the range on that? Can 1 over some number where x is between 0 and 1, can this ever be less than 1?
It'd be 1 and undefined, right? 1 and undefined.
Well, if x was 1, but I'm saying x is less than 1. So what happens when you take 1 over a small number less than 1? You get a number which is, this is not a hard puzzle here. Don't you get?
Can you repeat that?
I have a number that's between 0 and 1. It's a small number, it's a fraction. I take 1 over that number. What do I know about the size of this number? It's greater than 1. Yeah, it's going to get bigger. Right? What's 1 over 1? 1 over 1 is 1. So where the sine function is 1, the cosecant will be 1. Everywhere else, it's going to get bigger. What do you know? There's an asymptote here. This is a periodic function, so this is going to repeat. And then down here, the same thing is going to happen. Let me show you a better drawn version of this. Ah. So that's the cosecant function. They kind of look a little like parabolas, but they're asymptotic to those points where the sign is 0. So this is why I say it's a good idea to put in the sine function first. That tells you, the peaks on the sine function and the troughs tell you where the cosecant function has its minimum and its maximum. All right. Once again, where is this function not defined? Well, it's not defined with these asymptotes, which are pi n. That's where the vertical asymptotes are. What's the period of this function? This distance is pi. I know it looks the same, right? But so does the sine function, right? Sine function looks the same as the opposite. It's actually the period is from here to here. It's the same as the sine function. It's 2 pi, or if we have a b in the, it's just going to be 2 pi over that b value. All right. What's its range? Carlos, since you asked about this, what's its range? It's not all real numbers, is it?
I need one of those game show buzzers.
You want to answer one?
Maybe all real numbers, except for the ones negative ones.
Yes, all real numbers except, well, 1 and negative 1 are in the range. Yeah, it's, you could write that as x greater, absolute value of x greater than or equal to 1. That's its range. Okay, that's the cosecant function. I'm not going to dwell on this, but we can kind of do the same thing with the cosine function and get the secant function. Right? It's just the same idea, except now it's shifted over. It stays shifted. Okay. So a few more things about these functions. Actually, I just have a few more things to say about the tangent. The tangent has a very nice and respectable property you should be aware of. It goes back to your Algebra 1 days, right? So let's see how that works. I have some function, let's say 2x, or I'm going to graph y equals 2x. Y-intercept is 0, and slope is just 1 delta x, delta x, delta y. So delta y over delta x is 2. Right? call that? We call that the slope, right? Say m for the slope. Well, let's look at this triangle here for a second. It has some angle theta. We know that the opposite over the adjacent is what? It's just the tangent. Aha! The tangent of theta is just our slope, right? It's just delta y over delta x. So that's useful. If I gave you a graph like this, I said this is, I don't know, say 3.5, and the angle here is 42 degrees. And I said, I'd like to know the equation of this line. Well, at first that looks a little odd, but you go back to y equals mx plus b. Well, m is just the tangent of 42 degrees plus my y-intercept, and there's my line. So, just a useful feature. All right. Last thing I want to mention is just not really on the agenda. It's not really on the curriculum, but I think it has to do with something I think everyone's had a little experience with. Okay, so this is a map of the world. Has anyone not seen a map like this before? It's not the most beautiful version. This is called a Mercator projection. Does anyone remember this, like on their wall in 2nd grade or 3rd grade? You haven't seen this, Steve? Oh, okay, well, most people have run into it. And there's something peculiar about this map. It's known for having confused students for generations. You'll notice over here we have Greenland, right? Will be Greenland. And here we have South America. Looks like Greenland's about the size of South America. Okay, Greenland is not the size of South America. Greenland is pretty small. You'll also notice Alaska. Alaska's the size of half of the U.S., maybe even a little more, but Alaska's not that big. So this projection is known for having given students for centuries now, because that's how old it is, the wrong idea of the size of the continents. So the question is, why do we do this? Where did this come from? What is a Mercator projection? There's some other questions too. Like, does anyone notice we don't quite have on here the North Pole and the South Pole? I mean, you'd think, why don't we just make the map a little higher and put the North and South Pole on there? Does anyone know on this projection where the North and South Pole are? I mean, how far up they are? Trick question. Well, the North Pole would be up that way at infinity. And the South Pole would be down that way at negative infinity. Okay, so what the heck is with this crazy map? Well, it turns out this map has a really, really important use if you are a sailor, specifically a navigator. What happens is, the Earth is a globe, right? So if you have a map, and you're sailing the oceans, and you're here and you want to go there, and you think, aha, I'll just draw a line and I'll head in that direction. But in fact, that's not the straight way to get there. You actually have to follow what's called a great circle. The thing about the Mercator projection is that if you draw a straight line on the Mercator projection, it's a straight line. It's a great circle. And the way we construct it is instead of placing the axis for the y-axis at what do we have, 0 degrees, 5 degrees, and then 10 degrees, 15 degrees. Instead, we put these marks, which you can see, they get gradually further and further apart from each other. We put them at the tangent of this angle. So what happens is, if you think about it, where would tangent of 90 degrees be? Be off in infinity. That's where the North Pole is. So, anyway, I just thought this is just an interesting piece of, it's almost a piece of culture that most people don't know why we have this funny map, this distorted map, but that's it. It goes back to probably the 1600s and 1700s when we had sailors, you know, going across the Atlantic and maybe the Pacific using, they didn't have GPSs, they had sextants and maps. All right. So that's it for today. Thank you.